So we're on page 289, number 37. So we've got this meter stick. It always helps to visualize. We know that we're rotating about the 20 centimeter mark. A meter is 100 centimeters, so we know it's not in the middle. The middle would be 50. So here's the middle right here. We're going to be rotating about some axis right here. Now, right away, off the top of your head, you have to recognize that this is parallel axis here. Because the traditional way you're going to rotate is about the center of mass. This is not the center of mass here. If we go to look at table, so I'm referring to this table 210, we can see on table 210 that there are several formulas for rods. There are part C, D, and E. Part C assumes that the rod is rotating this way. So how can I demonstrate that with the meter stick? So let me grab a meter stick. So part C, the formula you're going to use for that one, assumes that you're rotating along the axis of the length. So there's one formula that the rod is literally like spinning this way. Okay, so this is the formula for C. It's rotating about the axis length. Then there's the one where it rotates like this. Okay, so we have to consider right away what's actually happening. So it says, blah, 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 the axis is perpendicular to the stick. Perpendicular. The axis of rotation is perpendicular to the stick. So here's the stick right here. So is it going to rotate like this, or is it going to rotate like this? First way or second way? Second way, right? This would be parallel to the axis of the length of the stick. So we know that it's going to rotate that way. So automatically, if we look at our table, we're going to jump to either one of two. Either choice D or choice E. Choice D has a solid cylinder or disc rotating about a central diameter, and choice E is a thin rod about the axis. Now in this problem it says treat the stick as a thin rod in parentheses. So that gives you the default right away. So we're going to automatically jump to table 10.2, and I'm referencing formula E. On table 10.2, I'm referencing formula E. So let's jot that down right away. And formula E tells us the following. The inertia is simply 1/12 mL squared, where L is the length of the rod and M is the mass of the rod. If you think back to physics last year, I'm sure, did you treat everything as massless rods or things that didn't have mass or didn't matter? Now mass does matter. Okay? Now we have to also recognize that this is assuming that it's spinning about, where is it? Right here. Here's the 50 centimeter mark. If I was doing this, that's the formula I would use right away. But it's not, right? That's not the case. Now we're spinning about 20. So we can see that this is clearly acting more than this piece over here. And you have to consider that, right? A fulcrum would always be in the middle. Have you ever done this one, by the way? Try this sometime. Take your fingers, put them anywhere on a meter stick, and start to move them together. Where will they always meet? At 50. It's kind of cool, actually. It doesn't matter what kind of an object you use. You take two hands and go like, assuming it's a rod, right? You go like this, you start moving your fingers together. They'll always meet at 50. I'm not doing that on purpose at all. Automatically meet at 50. Even if I start this one at 70 and this one at 1, you'll think that I'm purposely doing this. All right, I start to put them together. I'm not doing that on purpose. It's actually happening on its own. And it's kind of weird. You always end up in the center of mass. But that's just another side note. So our goal here is to calculate the rotational inertia. So what do I have to tack on to this?
Do you need the rotational acceleration?
I don't need the angular acceleration. All we're looking for is the inertia. We're not needing to solve with torques. You guys started torques recently, right? So you're probably thinking torque in the back of your head. This problem is only asking, it's cool, right? It's only asking you for the rotational inertia itself. So it's actually just asking you for I, but I'm saying this is not enough. This would assume that the object is rotating about the 50 centimeter mark.
Parallel axis theorem.
Yeah, what does the parallel axis theorem tell us? We have to add on to stuff always. It's a formula you can read off, or you can tell me physically what you're doing. Yeah, plus mh squared. Okay, and let's go over what this is. H is defined as the distance between the rotating axis that you're currently using and the center of mass itself. And the easiest way to do it, Arthur, you gotta listen. The easiest way is to go to your table. When I go to my table and I look at figure E in table 10.2, I can see that the axis is directly down the middle of the object. I wish you guys could see this as I'm seeing this. If you don't have this table in front of you, and I'm referring to this table right here, I go automatically to this figure, and I see that the axis about which it rotates is right down the middle. So I'm looking at the distance between the axis is rotating and the actual rotation we're going to have. So it's literally that gap right there, that gap of 30 centimeters. Okay, so all we have to do is plug in our formula, our values. We go through. We've got written values of, it's going to be 0.56 as the actual mass. The length of the actual stick, what's the length? What L are we going to use? 1, because it's in meters, right? We're not going to use 100 for centimeters or anything like that. That's going to be squared plus the mass times the distance between the center and that point. What is that going to be? 30 centimeters, which is really 0.3 meters. Say again? Give it a sec. It'll catch up. Or I'll just refresh it. But again, I have plus, this is squared, this is 1 squared plus 0.56, 0.3 squared. So you're literally just plugging into a formula at this point. This is probably the easiest kind of example you could expect, especially on like an AP exam. This would be very fundamental.
So for rotational inertia, for the first equation, you use the length of the entire run, not just the length to...
Correct.
Okay.
Yep. Whenever you look at the actual rotational inertia before applying the parallel axis theorem, L is the full length.
Okay.
Yep. Just like R would be the full radius of something, not some sort of difference distance. Here we go. Come on, come back. There it is. Okay. So again, this is the. I don't know what the answer turns out to be. I have it written down. I was working on it.
Yeah, but you have the answer. Can you?
9.7 times 10 to the negative 2. Is that what you have?
Yeah.
You have that too, right?
Yeah.
Why is that funny? Okay, my units are kilograms, meters squared. How do I know those are the units? Just look at the dimensions, guys. Kilogram times the length squared. Kilogram, length squared. Kilogram, length squared. They gotta match up. You can never sum together two quantities that have different dimensions. So that's another check always. If you're not sure if you did the right thing over here or over here, look at your units. Kilogram, meter squared. Kilogram, meter squared. It's gotta be the answer. Can't add two things that have different units. Okay? All right. That was 37. Let's take a look at 39. I'll read it, and I'll ask for people to maybe give a little help to start 39 at least so you know what you're going to be doing. So 39 says trucks can be run on energy stored in a rotating flywheel. A flywheel. With an electric motor getting the flywheel up to its top speed of 200 pi radians per second. That's its top speed. Suppose that one such flywheel is a solid uniform cylinder with a mass of 500 kilograms and a radius of 1 meter. Right away it says it's a solid uniform cylinder. Solid uniform cylinder. So we are looking at either choice C or choice D. Choice C or choice D. But we have to know how a flywheel works. How does a flywheel rotate?
Is it like this?
Yeah, it rotates about its own longitudinal axis. So it's choice C we're going to use here. 1/2 mr squared for that part. Now, let's see. Suppose that one such... What is the kinetic energy of the flywheel after charging? So here you're going to use kinetic energy for rotations. So what's your kinetic energy formula?
Okay.
Is that right?
Yeah.
Okay. It's analogous to linear kinetic energy. 1/2 mv squared, n is I, v is omega for rotation. So again, this is number 39, by the way. Same page. So what else do we know? It gets up to a top speed of 200 pi radians per second. You call that omega f or just omega for now? Is that what you would call that? Okay, I'm just trying to nomenclature so I don't confuse.
Is it 200?
200 pi radians per second. And it's important to recognize your units when you're using this. It needs to be in radians per second. So if you're given an RPM, convert to radians per second right off the bat. Okay, as soon as you're given anything like that. The mass of the flywheel, 500 kgs. That's a huge flywheel. That's like over 1,000 pounds. It's really
What
okay.
would they be using that for?
This is in an actual motor, but it makes sense because it's in a truck. It's in like you never see the front of like an 18-wheeler. That's where it's located. So it could be 1,000 pounds. And has a radius R of 1 meter? All right, the question is, what is the kinetic energy? So if it's asking what is the kinetic energy, what do you really need? Rotational inertia. Once you have that, it's pretty much right in front of you here. You got everything else. Okay, so you got omega at the top speed. They're asking for the rotational kinetic energy at that top speed. That'll be plugged in there. So really, all you need to figure out is I in this case. So we got to figure out I. What do we get for I when we do this? You have a number for me, or do you guys plug in variable first? You all variables first?
Yeah.
Okay. So we're going to be looking at, again, formula C, which is 1/2 mr squared. So we've got this formula here. 1/2 times 1/2 mr squared times omega squared. Okay, again, 1/2 mr squared is taking the place of I, so it's 1/2, 1/2. It's probably where you're going to see a 1/4 come into play there. I mean, that's it for this part. You just plug in numbers now. So these three values all go into the formula. Can I leave? I can leave you to that part, right? On your own? I don't think there's any use in me plugging in numbers. But omega can go in there. It's 200 pi. Make sure you square the whole thing. 500 for m. Radius is 1. Again, the concept here is that you need to be able to physically picture what's happening. So if you're not sure what I'm talking about right now, you should be looking at table 10.2 and look at formula C. Okay, 10.2, look at part C. That's what we're actually seeing here. We're seeing, like, imagine a disk that's rotating and spinning, and we're trying to calculate the amount of energy in that disk. The second part is really easy. The second part, if you know the definition of power, power is change in energy over time. So you know your energy change, it has gotten up to this. How much energy did it have to start when it wasn't moving? 0. So it's gaining how much energy? It's gaining this much energy. How? How does that happen? Because the power that was delivered to it. So the question is, once it gains this much energy, how long can it run for on that much? If it's using or consuming so much power. And part B asks, it says, if the truck average output power is 8 kilowatts. So right away, we got to write that down for part B. The power delivered is 8 kilowatts, or 8,000 watts. Okay, 8 kilowatts. All we need to do is use our formula. Okay, and simply, if you remember, power equals the change in energy over time. Power is the rate at which energy is consumed, really. And the only change in energy here is what kind of energy? Kinetic. You don't have to worry about gravitational, you don't have to worry about stored energy. So all we know is this kinetic here. And we're trying to solve for time, see how long this truck can run on this energy. So we'd switch time and power. The amount of energy consumed happened to be 4. This is the answer for the last part. 4.9 times 10 to the 7 joules. That was the answer for part A. And it's using a certain amount of power, which is 8,000 watts of power. That'll turn into 6.2 times 10 to the 3rd. And my units here are going to be seconds, I guess, because we're in SI units. And then if I wanted to convert that to minutes, I would divide by 60. Divided by 60, you're getting around 100 minutes. Around 100 minutes. Okay?
I got a different answer for part A. I don't know what I did wrong.
Well, look at your formula for part A. Did you use what we have in the top right there?
Yeah.
Did you use both 1/2?
Did you remember the other 1/2?
1.5 times 0.5 times 500 times 1 squared, which is 1, times 200 pi squared. Right?
The quantity 200 pi squared, yep.
Oh, the quantity 200 pi.
Yeah, 200 pi.
Actually, the 200 pi squared. Okay, yeah, that's not, okay.
Okay. That's why, if you notice in this class on the AP exam, if you do everything with variables, and you get it all right, and then you plug in the numbers at the end and you get it wrong, they'll only take off like maybe a small portion of a fraction of a point. So I recommend that you solve in variables. Like, is that what you've been doing all year? Yeah, I recommend doing that because on the test, it makes life so much easier. If you make a number mistake in the beginning of a problem in part A, and it carries throughout, you're going to get double jeopardized later on. So solve with variables whenever possible, and then plug in if you can. Questions on 39. Do you see how power and energy are related? Have you talked about this before? Power is change in energy over time. Think back for fun. So think about your physics course last year. Power was defined as the rate at which work is done. That's the definition of power. If you can lift 500 pounds over your head real quick, and it takes somebody else a lot of time to do it, you're generating or using more power. You're actually using the same amount of energy, but you're doing it quicker, so you have more power. Another way to think about power is the amount of electricity delivered to your house. And when you think about power ratings in a power company, although technically they measure energy, not power. The power is the rate at which energy is delivered to your house. So if your power coming in is more, it means you're just getting more energy over a quicker period of time. So in this case, you think about power, just think about it as how much energy you're using up or gaining, either one, to change over the time period. A watt, the unit of watts, is joules per second. So if you forget what to do here, this is joules, this is seconds. Joules over seconds is watts. So the dimensions are always going to match up. A watt is defined as a joule per second. That's something that's good to know, because later on when you look at your dimensions, if you're confused, you know where to go back and change it. All right. Let's look at 41. I think a few of these get a little bit trickier now because the other ones were pretty easy so far. 41, so you're going to probably need to figure, I'll draw it real quick. You've got a rotating axis, the origin. You've got a mass out here, M. This is the origin. You've got another mass, the same distance out, M. We know these distances are defined as D. We're told that it's rotating this way, according to the diagram. And the mass of the actual rod is capital M. So we've got the origin in which it's rotating, a rod of length D, capital M mass, attached to a small mass at a distance D away, another rod fixed to that of mass M, length D from the first point mass, and the second point mass is M located further.
So length in this would be the 2D?
Well, it depends on what you're looking at. We're going to have 4 parts of this problem. Think about this for a second. You've got one rod right here rotating about this origin. You've got a mass about the origin, another rod about the origin, another mass about the origin. So we have 4 parts of this problem.
Okay, we'll just do it.
Let's break it up into 4 parts and we'll see. So let's first read what it's saying, actually. So it says 2 particles with a given mass of 0.85 kilograms. Let's jot that down. Are fastened to each other and to a rotation axis O by 2 thin rods, each with length D 5.6, and that's centimeters, and the rod's mass 1.2 kilograms. These are just givens. That's all I'm reading to you here. The combination rotates around the rotation axis with the angular speed of 0.3 radians per second. Yeah, it's in centimeters, so 0.056 you can use. Measured about O, what are the combinations? A, rotational inertia. B, kinetic energy. Well, the kinetic energy is easy. Once you have rotational inertia, 1/2 I omega squared. It's just a formula you've been using. K equals 1/2 I omega squared. You've got omega, right? So part B is really simple as long as you do what? Find I in part A. So the first part is the part we have to consider ourselves with here. So let's take a look at this. Again, we're treating these like point-like masses at those locations, and those are our rods themselves. So we're going to have 4 different inertias. We're going to have a total inertia equaling the sum of these 4. Oops. Now, how do I calculate those values? What do I have to consider for that?
Further rods, would you have to use the parallel axis theorem?
Yeah, we have further rods here. So we have to consider that in this case, actually, they both use the parallel axis theorem, right?
Yeah.
Both rods do. The point masses, what do you do for those? What's your formula for any point mass to find its rotational inertia?
1/2 MR squared.
I think it's just, is it 1/2 MR squared or is it MR squared?
It's MR squared.
It's just MR squared, yeah. But it's just MR squared always. So these masses are easy. So I2 and I4 are going to be very simple. But I1 and I'm going to work my way out, okay? I1 and I3 are going to be the rods themselves. So we've got a rod from I1. Let's think about this for a second. This rod length is D. We know we're looking at this point, just so you're clear as far as which table we're looking at. We're looking at table, we said a thin rod. Did we assume it was a thin rod? 2 thin rods, yeah. So 2 thin rods means we're looking at table 10.2, section E. Table 10.2, does everybody have this table? You know what I'm talking about again? Section E. And that tells us that the rotational inertia of a rod about its center is 1/12. ml squared. So first, to start this problem, we have to consider that this first one has 1/12 ml squared, but m is really capital M, so let me specify the mass of the rod. What's the length of the rod? D. It's defined as D. So this is the first part of I1. I2 we'll add in a moment. What's the second part of I1? Again, this 1/12, not 1/2, 1/12. What's the second part of I1 going to read? So again, if this were rotating about the center right here, we'd be done. But it's not. It's not. We have to now consider the parallel axis theorem. What's missing as a result?
The mass, like plus another mass and half the distance.
Yeah, so we recognize that really this is the center of mass of the rod. So how far is this distance using the parallel axis theorem? It's going to be half of d. Right? That distance is half of d. And we know that the formula for the parallel axis theorem is mh squared. So it's the same mass of the rod. H would be half of d, and that number is squared. This is all for rod 1 right here. I'm going to break it down again. I'll point I'll point on the video so you can see if you watch it later. Here, we've got the rotational inertia of a rod, assuming it's rotating about the center right here. But since it's not rotating about the center, and it's rotating about the origin or this rotational axis here, we have to see how far away this is. That's d over 2. That goes in right here. And since it's the parallel axis theorem, we're always going to tack on mh squared. We always add that on for the parallel axis theorem, h being the length between the center of the rotation of the original diagram and where we're actually rotating. Now again, that's just the first rod. That's all that is. What would the first mass be? What would this first mass right here? How would I incorporate for I2? How would I incorporate the rotational inertia of this mass alone? What do you got?
Like the mass of that and the rod.
The mass of that?
Oh.
The rod is already taken into account.
So the mass of that times like d then, right? D squared.
Yep, very good. Again, the rotational inertia of any point is mr squared, where r is really the distance, right? Okay, so what's the distance between the mass point and the origin? It's just d. The same length of the rod is where this mass is fixed, because it's fixed at the end of this rod. So this length is d. That goes in right here. It's really mr squared, but that's all I2 is. I2 is very easy. I3 is pretty easy also, except now we're just a little bit staggered further out, right? See how we're further out for I3 and I4, the same thing. We're just further out from the rotation axis. So this is mass 1. I'm going to keep adding to that. Now, let me zoom out a little bit so we can see this still if I move up. To that, I have to consider the fact that we need to now add the second rod. So this rod right here. What's the rotational inertia of a rod? We just said it. What is it?
1/12
Yeah, 1/12 md squared. So is that going to change? No, because these are the same exact rods. They're identical. So I know that the beginning part is the same. That's for sure. But now, how far is the center of the second rod from the rotation axis? 3/2 d, or 1.5 d. So this is going to become plus m times 3d over 2 squared. Again, this was the first rod. It was at a distance of d away. The next one is a full d and another half d. Full length d from here to here, plus another half to here. That's 3/2 the length of d, or 1.5 d. So that's where this comes into account, and you square it. Again, this is the rotational inertia of a rod. This is incorporating the fact that the actual rotation axis would be here, but really we're rotating about here. So we account for this length here to here as 3/2 d, square that, and multiply by the mass, because the parallel axis theorem tells us to add on mh squared. Okay? I'm sure you guys probably, and if you did or didn't, you don't have to answer, but I'm sure you may have talked about or read your book, the whole derivation of where the parallel axis theorem comes from and how it works. But as far as the test is concerned, you're going to really have to apply a lot of this stuff. So I wouldn't, like, if you're struggling to even understand, like, why do I use the parallel axis theorem? That's actually not as important, believe it or not, right now, as getting the work done. Okay? So even though you might be, like, fretting about the fact you don't know, well, why is it plus mh squared? At this point, if you've already learned why, which you probably have gone over either by reading your text or in lecture, at this point, don't even worry about why. Just worry about how to apply it now. Okay? Because when it comes to the day of the test, if you want to do well in this exam, you need to know that you're incorporating an h squared. I don't think they're going to ask you, at least when I took the exam, it was never asked why do you have mh squared or where does the parallel axis theorem come from, but how to actually apply that in a problem. Okay, so that's the second rod or the third part. And then finally to that we have to add the last mass. How do I incorporate the rotational inertia to the last mass? How far away is the last mass? How far away is it? 2D. 2D. So I have to take m, which is the mass of the second one, times the distance away, that quantity squared. Please remember, you've got to square the quantity. Okay? Make sure you square the quantity 2d, not just the value d. Now you just plug in. Okay, all of our variables were given in the beginning. We defined them all at the top earlier. When plugging in, you will get, what did I get here? Oh, Lord. 0.023. Again, same units as earlier, kilograms times meters squared. Remember, please, that your D value was given in centimeters as 5.6. So if you didn't get this answer, it's because you forgot to convert that to 0.156. And because you're squaring that several times in several spots, your answer will look nothing like this. Remember how in class you forget to I forgot to move the decimal over so it's off by a factor of 10? Your answer would be 2.3. That's not going to happen anymore. Because if you're off by a factor of 10 or a factor of 100 in this case by not converting, and then you have it and square it, and then you 3 have it and square it, and then you square it, you know what I mean? It's never going to be just you're going to see a decimal move. So you're not going to know that what you did was wrong, or what you did wrong was not forgetting to convert based on the answer alone. Because if you check the answer in the textbook in the back, and let's say, this is the answer in the back, and you got 2.3, that's an indicating factor, old school with physics when it was easy, right? That, I just forgot to convert. I didn't move the decimal over. It's not going to happen anymore. Your answer won't be off by a factor of 100. It'll be off by some arbitrary value, not arbitrary, but some mathematical constant based on all of those squaring factors occurring. Part B simply says, find the kinetic energy. If the speed, rotational speed or angular speed is 0.3 radians per second. So that's actually, really simple. You're just going to take 1/2 I omega squared, 1/2 times I times omega squared, omega 0.3 squared. Okay, that will give you 1.1 times 10 to the negative third. Okay, my units are joules. Yeah, my units are joules because we're looking at kinetic energy. So what you should have recognized so far over the last few examples is that when an object does not rotate about its center of mass, you have to take into account the parallel axis theorem. When does that always come into account? As plus mh squared. If it's a point mass, always remember mr squared, which is, you guys used this earlier in here to come up with all of these. Did you derive any of these, or did you go right to the tables for them? That's probably the better move. I would have done the same, because the derivation for all of these involves a whole lot of integrals and calculus, which is not difficult, but very time consuming. So if you want to get to the point this year where you guys are practicing more, I would have gone right to the tables also. It's interesting, side note, as an engineer, when we were I was a mechanical engineer. When we used to study, the mechanical engineers used to do all the heavy math. We would do all of the derivations, show where everything came from. And then the civil engineers would just use tables and pull them out of the tables. So we used to, not that if anybody's parents is a civil engineer, they're very smart, I'm sure. I'm just saying, when we were in college, we used to always joke about who was the smarter engineers out of the group, and we would mess with each other that the civils, they didn't do any math. They right out of tables, and it's true. A lot of their work comes right out of tables. It comes out of tables with stress strain curves, or even deflections of beams. It's all out of tables. Where does that stuff come from, though? It comes from calculus. You can see it here because you have this formula from the table also.
So how does that make you
It doesn't really. It's just more like a bragging thing. Yeah, it was just exactly. It was a nerdy thing, yes. But if we got to brag about something, that was it. Yeah, it wasn't really anything better. All right, 43. 43 is interesting. I was reading through it and I liked it because suddenly you're not looking at a rod or something with simply a radius. Now you're looking at something with 2 dimensions to it, and also a thickness. See, so 43 we're looking at, right? Is that the right one? 43? Yeah. The uniform solid block in figure 10.3.8 has a given mass. So let's jot that down right away. The mass is given as 0.172 kilograms. The actual solid looks like the following. Okay, it's rotating about the rotation axis that is along one of its edges. There's the rotating axis. This is defined as A. This is defined as B. And the height is defined as C. Okay, that's what we're given in the diagram. We're given values of A, B, and C. A is 3.5 centimeters. B is given as 8.4 centimeters. And C is given as 1.4 centimeters. The question says the following. Calculate its rotational inertia about an axis through the corner and perpendicular to the larger faces. The larger faces. So, I mean, they put that in there, but they don't need it in there because the diagram was given also. But just so you're familiar with that. Okay, the larger faces. So we're trying to figure out the rotational inertia as it rotates. Why is this a little bit difficult? It's not really that difficult, but there's one little hiccup along the way. It's 3D, okay, but it turns out C doesn't even affect the problem. Right? C we don't need to utilize at all in our formula. If I go to table 10.2, look at I. There's no C in the formula. So it turns out we don't need the thickness of the plate. Right? This is like a steel plate, if you will. So it's 1/12 m times quantity A squared plus B squared, but what's the problem? Yeah, here's the center of mass right here. That's where it assumes it rotates about in table 10.2, figure I.
Oh, but it doesn't do that.
But it doesn't do that, so your question is, what is this distance here? It is a triangle. View this from above, please. This is a right triangle. It's hard to draw it. You see the right triangle involved there? Half of A is the base, half of B is the height, H is the actual hypotenuse. Now, a little bit of a shortcut for you. You would normally calculate H, correct? And then utilize it. But since it's the Pythagorean theorem, aren't you going to get H squared and then have to square root it? But then later don't use H squared anyway? So there's no use to take the square root of H in this case. And let me show you what I'm saying just so you're clear. So the rotational inertia of a body like this is going to be 1/12 m times the quantity A squared plus B squared. That's the rotational inertia of this, assuming it's through the center. But again, because it's not through the center, we have to include this. Okay, where we're looking at the actual parallel axis theorem, mh squared. H is that length. Since I can utilize this formula here, I could say the following. Does everybody see that? That's my Pythagorean theorem. Half of A squared plus half of B squared equals H squared. But look later on. Are you utilizing H squared later on? So don't take the square root and then put it back in. Just replace the expression, the substitution method. Okay, so replace H squared at the bottom in that formula with A over 2 squared plus B over 2 squared. And this is going to be, let's write it as A squared over 4 plus B squared over 4. Okay, I'm just going to square those fractions, giving me A squared over 4 and B squared over 4, replacing that for H squared. And that's your answer for this one. Okay, all you're going to do is plug in at this point. So again, this comes from the actual formula in 10.2, in table 10.2. This is the parallel axis theorem portion. Okay, just keep in mind that you're doing that every time when you're not rotating about the normal center of mass. I'm trying to figure out what I can get as a number. Let's see. Oh, you know what? So I was looking at your solutions for this, and they simplify things. You could simplify this a little bit further, obviously. Right? How could I simplify this? I could take out, this is a 1/12, right? M, A squared plus B squared. And this over here is really, God bless you, 1/4 M, A squared plus B squared. Right? Isn't that really what's happening? So 1/12 and 1/4 will give you 1/3. Right? So this is going to be 1/12. This will be 3/12, 4/12, which is 1/3. So your final answer would just be 1/3 M times the quantity A squared plus B squared. So you'll end up getting the same answer whether or not you simplify. It really doesn't matter. And this will come out to be, again, think of this here, right, as 3/12. 3/12 and 1/12 is 4/12. 4/12 is 1/3. I'm killing myself, right? I did that earlier when I had the half. I meant to put 12. Thank you. We'll get, plugging in, 4.7 times 10 to the negative 4. And again, units of kilogram meters squared. Oh, this is interesting. I'm reading this little note that is written down here. Recognize that this answer is greater than the previous answer. Why is that? This answer is greater than the original formula. Why does that happen every time? Why, when you incorporate the parallel axis theorem, you always get a greater answer? Besides mathematically, you're adding something. I know that. Physically, why?
Because like, even when you're like opening a door, like the farther away you get, like the kind of like easier it is to, or like the greater.
The further the mass
Yeah,
is, right? The further the mass is spread out, the more moment of inertia it has, which is really pretty much telling you like it has more mass. Remember mass and inertia? Inertia physically is defined, or mass is defined as the measurement of inertia of an object. It's actually its definition from physics last year. So if you think about it, if an object has more mass, it has more inertia, it has more desire to stay at rest. It's harder to push an object with more mass because it has more desire to stay at rest. Mass is a measurement of inertia. Same thing here. We call it the moment of inertia. Moment of inertia because if I'm holding this like this and I want to spin it, it's not that hard, right? And now I attach a bunch of heavy weights on the end and then try and spin it. Now instead of the mass being distributed evenly, you got a lot of mass on the end. It's going to take a lot more for me to turn this because the moment of inertia, its desire to remain at rest is greater. As soon as you spread out the mass further, its moment of inertia is the desire to stay at rest. Inertia, an object stays at rest, when at rest, an object in motion stays in motion. So moment of inertia is simply the rotational mass. That's all it is. That's why you replace mass with I all the time. An object that has more mass, you can't move as easily. An object that has more moment of inertia, you can't rotate as easily. It's the same thing. They're analogous to one another. Okay, so the more moment of inertia, the harder it is for you to get something moving or to move it from rest. Or, if it's already moving and you want to slow it down, the more moment of inertia, the harder it is to slow it down, actually. That's why if you think about an 18-wheeler, those trucks, they have huge wheels on them. The braking force necessary to stop a truck, besides the fact that it's got a lot of linear mass moving, the braking force is larger also. You have to consider the fact that everything is rotating, and they're all bigger objects that are rotating as well. So to slow down that wheel that's rotating with a bigger axis with more spread out mass, it's going to take more braking force. All right.